So again, thank you for the invitation. So now we have seen much about what you can get about some formal axioms on fiber triangulated category, and I want to give you an example as they have appeared in the talk. I will consider a theory of Wojcicki's motivic complexes. Which leads to his definition of the motivic Eilenberg-MacLane spectrum. So the theory is based on several beautiful ideas about algebraic cycles, and in particular on the work of that was done by Suslin and Wojcicki on relative cycles. So maybe the plan will be definitions and basic properties, and then I will go on the problem of localization and the solution that exists so far. Okay, and so the definition relies on this, especially if you want to work over singular bases, relies on this theory of relative cycles by Suslin and Wojcicki. I will focus on a particular case, finite case. So in the classical approach of motives by Grothendieck, you used correspondences, algebraic cycles, and the fact that you can compose them by using intersection product. If you want to do the same thing but relative to any base, and as you've seen in the case of duality, the interest of this is to work with singular base, then you have to understand how to intersect cycles for singular schemes. And this is the whole purpose of this theory of relative cycles. So I will only present the idea because I have not much time. So let me consider the basic problem like that. I consider, say, alpha zy a cycle, algebraic cycle, in some scheme x. Noetherian, say, that's all I need. And I will take the assumption that I have some map x from z from S to S, F, and such that if I consider any zi, the structural map here is finite. Let's call it Fi. Okay. Now I want to define, in some sense, a pullback with respect to S of this cycle alpha. So assume you have a scheme here, and I will consider only a special case where the scheme is just the spectrum of a field. Okay. The problem is to define something like that, tensor Sk for this individual zi cycle in, if I write this S, say, in XS, so-called fiber of this map F in XS. So usually you cannot do that easily without any assumption. There is an assumption that guarantees that you can define this cycle here when Fi is finite and flat. And the idea of Suslin and Wojewicki is to somehow restrict to that case. So how do you do that? I will assume that, say, Fi is finite. So the Zi are closed integral schemes, right? So I will assume that Fi is finite and dominant over an irreducible component of S. Okay. When that happens, I say that Fi is finite, equidimensional, for short.
So you mean restricted to Zi?
Fi, yes, Fi is Zi in the map from Zi to S. So I just assume that the map Fi is dominant. And then in this case, I can use the so-called platification theorem or flatification theorem of Gruson-Reynaud, which tells you the following. There exists a blow-up of Si such that a strict transform here in X plus S tilde, say, verify the fact that this map here, the projection to Si, is not only finite but flat also. Okay, so this is a blow-up, and this uses the flatification theorem of Gruson-Reynaud. Okay, then I have my point here, spec K. What can I do is I can always find a finite extension L of K such that the point here lifts Si tilde spec L. As I said, now I can define this Zi tilde thing. So I just take the fiber product in the category of schemes and take the associated cycle. So this leaves in XS extended. So XS is a K schemes, and you can extend the scalars to L. Okay. And then, okay, say I can do that for any index I can find a big blow-up such that each proper transforms are finite flat and an extension like that. And so I can define some alpha tilde CL, some I and I cycle associated to this. Let me write tensor, sorry, the fiber product is taken over SI. Okay.
Assuming the spec L is a point of SI tilde.
What?
Spec L is a point of SI tilde.
Yeah, but you can always find such a point. You take a finite extension like that. Okay, now there are two problems with this strategy. First, how to descend alpha tilde L to XS. And second, if you can do that, does the result depend on the choice of S tilde? S. Sorry, this is not S. Okay, the S was fixed, and the I appears only here. Okay. So let me address the first point. How do you descend to spec L? And this uses a so-called Galois descent, and this is the first. I think this was due to Weil, this principle, and then it was the notion of descent was extended by Grothendieck and Deligne for cohomological properties. So Galois descent of algebraic cycles. This is a kind of principle, and it tells you the following: if you have X, a scheme of a spec K, and L over K, a finite Galois extension, but not necessarily separable. Then with Galois group G.
On normal extension.
Normal, yeah. When you consider this change here, XL, then you have the following. If you are given alpha bar, a cycle in XL, then a necessary and sufficient condition so that it descends is that alpha bar, if alpha bar is G invariant, so the Galois group acts on this scheme, and you ask that alpha bar is G invariant, then there exists a unique cycle, alpha 0 cycle in X, such that so-called this phi upper star of alpha 0 is the inseparable degree of the extension D times alpha, where oops. Okay, so that you have lived your cycle, alpha 0 is equal to phi upper star 1 over D alpha. So to live cycle by this Galois descent, you have to divide by some integer here, which is in general an inseparable degree. So in particular, it's the power of the characteristic of spec K. So, but, in this procedure, you see that what? Phi upper star, so alpha. Alpha 0. So I alpha 0, alpha bar, alpha 0. No, yeah. Okay. You want to lift, you want to descend, the cycle alpha bar, and you can find this. So, so you see, if you have a set of points in XL which is permuted by G, then you can take the image, take any point. But if you take the pullback afterwards, then you'll have each point will be multiplied by the inseparable degree of the extension. This is quite easy, in fact. Okay, so let me go back here. So you see that you can solve this first problem 1 here, because you can always assume that the extension L over K is normal by taking a bigger extension. And then because of this procedure here, the cycle that you get here will be invariant under the Galois group of the extension. So the answer here is yes. and you get a cycle, get alpha tilde, a cycle in a special fiber, which a priori depends on S tilde, and the definition I'm going quite fast, but the definition of Susin and Voevodsky is the following. I can say, this is after Susin and Voevodsky. They do not use this terminology, but I will use it. We will say that the cycle alpha over S is special if alpha tilde, this is a bit, does not depend on a choice of S tilde. So this is not a perfect definition, so let's say this is after bracket. We have a much nicer condition than that, but it's equivalent to this assertion. Okay? And those, in this case, you can put alpha, I use this notation, alpha base change along this point, spec k, is equal to the alpha tilde, well defined. Okay, now, so I have defined a pullback here. The thing is that this cycle here, even if I've started by a cycle with coefficient in z here, as you have seen, I have to divide by the characteristic of spec k. If it's exponential characteristics, say. Cycle in excess. Okay. So let me add a definition. We will say that alpha is z universal, or let me. If for any point this alpha has coefficient in z. You see that can happen, so it depends on the coefficient that you have chosen here, for example. If you have well chosen your coefficients, it might happen that all these denominators will cancel and the cycle will stay integral. Okay, once you have defined this notion just for one particular point on S, then if you have any map for any f from T to S, if you have alpha or S, a special cycle, you can define something like f upper star alpha, which is a cycle in X cross ST here, because actually, so to define this cycle, you just need to find the appropriate multiplicities, and these multiplicities that depends only on the generic points of T, which gives you and then looking only at the generic points of T, you reduce to the case here where you have spec K to S. Okay, this is the idea. Okay, so now, as you see, these two conditions here are a bit abstract, but there is a very big important theorem of Susin and Voevodsky that I mentioned here to say that it's a reasonable theory, which is the following. First of all, with this condition here, you assume that if S is geometrically unibranch, for example, normal, so it means that this scheme is integral or a direct sum of its reducible component, and this property stays true after any étale-based change. Okay. So if S is geometry unibranch, then any alpha of S with this condition finite equidimensional is special. So that the property here, that it does not depend on S tilde, will always be true if you have this this notion, this property. And the other one, which is even better, is that if moreover S is regular, then any alpha over S finite equidimensional is not only special but also the universal, and the multiplicities of the intersection multiplicities involved in this F upper star alpha are given by the Tor formula. Okay, so we get back to the more classical things. Okay, so that's all for this this beautiful theory. Now, once you have a good notion of base change for cycle like that, then you can you can obtain a good notion of finite correspondences, as we have seen, over any base.
Degree D there. So, is it inseparable degree?
Yeah? Yeah, sorry, there's an I here. So it's a power of a characteristic of K.
When you say that the extension is Galois, you mean?
Normal.
No.
Sorry. Okay, so now I have to be quicker for the details. One can define a category. So I will denote it like that. Je core S. Object are S schemes which are separated. So this is important here of finite type. And morphisms from X over S to Y over S are cycles alpha in X cross S Y such that alpha over X is, so first finite equidimensional special and the universal. Of course, you can, if you change, instead of taking Z, you can take any subring of Q, and it will improve this property here. For example, if you take Q universal, always happen, of course. Okay, so because of this existence of good pullbacks, then you can deduce there exists a composition product. I do not give details because I have no time, but it's quite quite easy. And let's mention that then, so you get a good category. With a graph functor, as we have in the case of a classical case of a field. So this goes from the category of separated S schemes to this category of correspondences and to a morphism X to Y. It associates the cycle, write it like that, of the graph of F. And because the graph of F is an isomorph, a projection to X is an isomorphism, it will satisfy so this property, obviously. Okay, we have used the fact that schemes are separated to get that this graph of F is closed. Otherwise, maybe you could do something, but it's trickier. And also finite type, otherwise it would be, there will be eventually an infinite sums of irreducible components. Okay. Okay, once you have that, then you can develop the theory of Wojcicki, of Schiff transfers. Actually, he has written that in the case of schemes over a field in one of his papers with that degree of generality. But so for this definition, I take P to be either the category of smooth schemes over S or the category of all finite type smooth schemes over S or finite type separated schemes over S, and in a P core S obvious category. I can define correspondences for any singular scheme, so I can also define them for smooth schemes. And I will define a T sheaf with transfers over P core S is, as usual, an additive contravariant functor from this category to, say, category of R module such that if you compose F with a graph functor, then this is a sheaf for the topology T sheaf, and I restrict to T. Well, T can be more or less any topology, but I will use Nisnevich et al. CDH and H when P is this. Okay. So the resulting category, let me write this category of sheaves on T on P core SR is quite reasonable. So actually you can show, so there is again some work here, but you can show that it's Grothendieck abelian, but also it forms the collection of these category for S in the category of Noetherian finite dimensional scheme form a P fibered Grothendieck abelian category. So recall, this means that we have operation like F upper star, F lower star, P lower sharp for P either in the first case in P, let's say. So either smooth or separated, and tensor product internal on. Okay. Then I'm going fast. So all these things have been checked in the book I mentioned in my last talk with Sinski and myself. But you can also define a good model structure on the category of complexes. Actually, it's the analogous model structure that I define for DA1. So that in the end, let me write this. There exists a model structure called T-local on the category of complex of sheaves with transfers for any topology like that. So here, for this assertion, you really need that T is finer than Nisnevich topology, but you use the same trick than Vygotsky did over a field to get all these properties. T-local, yeah, exactly like the one without transfers. And so in the end, we get our last definition. You can define dm effective. Let me write it like that. S of R as the A1 localization of the derived category of sheaves. At this time, this is for Nisnevich topology on SS core R, and the stable one is obtained by P1 stable category associated with this dm effective. Okay, and in the end, what you get is that this category, dm R, is pre-motivic, as I call this, is triangulated. Category, so you can derive all these functors here. So, and it's obviously stable and homotopy invariant by construction. Okay. All this is quite, so it's formal, but it's based on some huge theory. Just a remark or an example. If you want a kind of computation of this category, so you can define the constructible part of a category. Let's start with the effective one. So this is the full subcategory here, generated by motifs of x over s which are smooth, and you twist only with positive integer. Then this category is really equivalent to what Vygotsky defined as the geometric category. So it's the category of complexes up to homotopy above this category, which is additive, by the way, because morphisms are abelian. And direct sums are just given by direct sums of schemes. And you localize with respect to A1, homotopy, and the BG property or Nisnevich property. So formally, you get this isomorphism regardless on S here, and then the non-effective one, constructible non-effective one, is just obtained by taking the pseudo-abelian envelope of this category where you are formally inverted the Tate twist. Okay. Among the other formal properties of this category, is the fact that you can derive from the graph functor a pre-motivic adjunction, which has already also appeared. So this goes like that. So you had the graph functor, write it only for smooth schemes. It will induce an adjunction between the category of Nisnevich sheaves without transfers of R modules and the category of Nisnevich sheaves with transfers. So there is an obvious functor which is composition with gamma and left adjoint gamma upper star. So you have to prove something for the existence of this adjunction, but it's well behaved. Again, it will define an adjunction of so-called SM fibered abelian categories. So this functor will commute with all the left adjoint, and it can be derived because we have used the same procedure for DA1 and for DM. You will get in the end, I don't put the derived, using the derived functor here, you will get adjunction like that between DA1 and DM. Something that you have already seen over any base. And I just recall that you have also an adjunction between SH and DA1. So this is the Dolkan, like that, sorry. Okay. And the Dolkan, derived from the Dolkan equivalence. Okay, so that following Wojewicki, you can put you can define H R S. This is just K of gamma lower star of constant object. Okay. It's clear that this is a strict, say it like that, ring spectrum. Meaning that because these are derived functors, you can actually get a monoid object in the underlying category of symmetric spectra if you want. So it has a good product structure also. And it's clear that this object represents in SH the cohomology defined by X group, extension group in DM of R. This is just a game of adjunction. Represents, so maybe I should write it. Wojewicki's motivic cohomology. Say for S, so we have H, R, S, S, and M is the same thing as the in DM, S, R of constant object, twisted M times, shifted N times. Okay. So maybe I should write Wojewicki's motivic cohomology, but okay. Okay, everything is well, but this is at the moment completely abstract. And for example, there is a big missing property. If you have followed, this is the so-called localization property for this category. So what can we do? And as you have seen, without this property, it's impossible to, at least we don't know how to get the full six-functor formalism. But yet we can do some basic things. There's a proposition which is not so difficult to get, that we obtain with Szysinski, that is the functor gamma lower star here is conservative and commutes with the functor J low sharp for J in open immersion. Also, you can prove that if you consider y from z to x, a closed immersion such that P and Q are smooth. Okay, then gamma upper star commutes with y lower star. These are more or less general tricks that you can get from the definition, and it already implies something interesting. So you see that this functor gamma lower star not only commutes with J lower sharp, but formally also it commutes with any F lower star when F is proper, or any morphism. So the first point here, one, immediately implies the so-called support property for dm, which implies that you get, you can construct this pair of adjoints. Okay, and if you are careful enough, you can show that the second point implies at least that you have a base change formula, the projection formula, and the projection formula for any morphisms, any separated morphisms of finite type between smooth schemes, between smooth, say, S schemes. Okay, if S is some base which is chosen like that. Okay, but unfortunately this is not sufficient to get important properties such as the duality, the Grothendieck-Verdier duality theory. And at the moment we cannot prove the localization property for dm, so this is more or less a dead end. So anyway, we were able to do to solve this problem again with Szysinski in some particular cases. In my last quarter, I want to describe you these two cases. Before doing that, maybe I'll state the problem. localization property for dm. That might not be, let's take z coefficient. That might not be solvable, I don't know, but the problem is the following. You have x over s, Sn is scheme, Noetherian, I, a closed immersion, of x over s smooth, you look at the sheaf with transfer represented by x. This is just this pre-sheaves, finite correspondences to x. Okay, so it's an explicit group. You can define this pre-sheaf x minus xz as an obvious co-kernel of sheaf. Sheaf of pre-sheaf does not change. And the problem is to prove that you have a canonical map from this pre-sheaf here to this one here, while over star z transfer over xz, and you have to prove this is weak A1 equivalence. You can even work stably if you want. So this is the localization property in DM effective. Say it like that, I think. Okay, and this problem is very explicit, and in fact it's in some sense close to the localization problem for higher Cho theory. So I just wanted to advertise this problem. It's quite concrete and maybe it can be solvable. So we have a kind of solution for this problem in some particular case, but it's not. There's no direct proof of this fact. What?
What is the topology?
Nisnevich. But this is a good point because changing the topology might make this easier. Maybe I should say another point. So if you try to run the proof of Morel and Voevodsky to this, you remember maybe I told you that you restrict to the case of that case of x smooth here, and you add a section like that phi. But because you use finite correspondences, the only thing that you can do is restrict to this case here. You have here a finite equidimensional, which will correspond to some finite correspondences, and you have a square like that. And once you have this situation, you cannot do the trick that I have given. So even if you assume that S is Henselian, that does not tell you much about this section morphism here. Okay. And at least us, we were stuck here. Another remark, maybe.
The base scheme is just a perfect field or a field?
Well, of course, if S is the spectrum of a field, there's no closed immersion. So, but if S is over a spectrum of a field, it does not really simplify the matter. Yeah. So as I said, I think this problem is quite close to the localization problem for higher Cho group. So, for example, this problem was solved by Mark Levin for Dedekind ring. So maybe for Dedekind ring you can do something, but I don't know. Another remark. There is, so in his paper on, after his talk on in the ICM, Vygotsky has stated a list of open problems in the motivic homotopy theory, and one of his conjecture this is the last one in the paper on open problem, is that this ring, the ring spectrum, the motivic ring spectrum, HRS, is stable under pullback. So it means that whenever you have a map from T to S, the map F upper star HR of S to HR of T, so there is a canonical map like that. Yes, is an isomorphism. And the fact is that if you have a localization property for I, a closed immersion, a given closed immersion, say Z from S, for dm, then it implies that conjecture is solved for this particular I here. And so if you have localization for all maps in dm, then you are able to prove this in general for any morphism F. So, yeah. But still this conjecture is still open. Okay, so what can we do, say, to overcome this localization property? So we have essentially two solutions. First solution is to use rational coefficients. And second solution, as Panin has suggested, is to change the topology from Nizhnevicha. So I will just, I think many of you have seen the case of rational coefficients, I think. So in this case, we are in some sense safe because fortunately we have several different presentations of a category of motives of Beilinson as conjectured by Beilinson with rational coefficients. So we have first trivial facts. If you consider the stable homotopy category with rational coefficients, then it's actually equivalent to the A1 derived category because of Serre's finiteness of stable homotopy groups of spheres, essentially. And also with rational coefficient, we have a good model for motivic cohomology, and we have seen that we talk. If you take KGL, the ring spectrum which represents K theory, then it splits canonically, say by Chern character, as a direct sum over all integers of some ring spectrum HB I to I, and HB represents, say, Beilinson version of motivic cohomology with rational coefficients. Okay, so instead of a big definition, I will give you a big diagram which give you a presentation of all possible variants of rational mixed motives over S. So first of all, you can say, well, so KGL of Q is a sum of motivic cohomology, and for mixed motive we are interested only on things which are seen, which correspond to this motivic cohomology. So there is a trick to look only at equivalences of ring spectra which are seen by a ring spectrum, which is called boost field localization, and you can apply this to stable homotopy. So you can boost field localize the derived category, the A1 derived category, with respect to KGL. So this means that a morphism of ring of spectra will be an isomorphism if and only if, after tensoring with KGLQ actually, it's an isomorphism. And so this is a reasonable category. Why? So first of all, you can prove using more or less this isomorphism. Maybe I should mention Ryu here. You can show that actually this category is equivalent to the category of HB module, or S. Now you know that HB is an oriented ring spectrum, and in particular eta acts trivially on this category, and using results of Morel on actually the computation of the homotopy group of S0, you can show that this is also equivalent to dA1SQ plus the plus part of the A1 derived category we have seen, so that's the same thing as the plus part of stable homotopy. And you can see that this is the same thing as dA1 etal SQ, a category considered by Ayub before us. Here, no assumption. Not here, infinite dimensional. But
You said that you use some computation by Morel.
what?
When you said that you use some computation.
Yeah, but you have seen that with localization I can restrict to fields. So you can also avoid the problem of infinite fields by using dévissage. So this is okay. So I just use pi naught S naught over the computation of this over a field. Once you have the etal topology, you can actually show another thing, that this is equivalent to the category that you get by using H sheaves. So I will write this DMHSQ. So actually, this is more or less the category that was considered in the thesis of the PhD thesis of Voevodsky. So it means that instead of looking at the etal localization of the A1 category, you can look even at the H localization of a category. And in the end, back we get our results. We have to assume that S is geometrically unibranch for this last result. But I think this is, maybe we can avoid this assumption. And then we get back to this category, S of Q. Okay, this is approximately the way we prove that. So that in the end we have not proved anything for this category except this equivalence, but because this one, all these ones actually here satisfies localization, we get that this category satisfies localization for these geometrically unibranch schemes. So we have not directly solved this problem, but quite indirectly by using some triangulated argument. Note that there are interesting corollaries that were not known. Maybe I just cite one. If you take the Voevodsky's motivic cohomology of S with coefficient in Q, S regular, using this equivalence and say this one, for example, what you get is that it's really equivalent. So this is coefficient Z tensor Q I guess this is equivalent to the relevant gamma graded P. So this is I k to I minus n SQ. So this property was known when S is more or less S regular over the field, but we get this for any regular base. Okay. I have not much time, so maybe I will finish orally. So as you see here, so when you look at the H topology, it's not a canonical topology, and you can see that the H sheaf represented by some smooth scheme X over S is actually, you can compute this object, and it actually coincides with the sheaf represented with rational coefficients in this category. So the H topology makes transfers appear. And in the other end, the H, so this DMH is you could take the category of sheaves with transfers for the H topology if you want. So it tells you that changing the topology might help to prove the localization. So one thing that we have done with Szyński is that we have looked at the category DM but localized for the CDH topology. If localization holds, remember that it implies the CDH descent. And what we have proved is that if you use CDH topology and using de Jong results, if you restrict to K schemes and invert the exponential characteristic of the fields, then you can actually prove localization and more. So maybe a solution to that localization property is really to use the CDH topology. But we have made that work only with a base field. So I think that the model of motivic homology by Wojewski, so it's close to algebraic cycle, and so this is interesting. For example, we get for free on these groups trace maps for very general finite morphisms, but still it's not so close to the Chow group. However, the localization property will imply that the Borel-Moore version of this homology in degree 2 and n will coincide with Chow groups, for example. So it's already related with classical algebraic cycles. Nevertheless, I should mention that there are other approaches to the problem of defining a good category of mixed motifs integrally, which models Chow groups, for example. And this was done by Markus Spitzweck, where he defined another version of a motivic cohomology ring spectrum over a Dedekind ring by using, instead of Susin-Wojewski's model, by using higher Chow group and results of Levin. So I think the interplay between the two approaches might give new results in this theory. Of course, the problem is that, for example, we don't know that there is a ring structure on Chow group over regular schemes without a base field. We don't know. This was asked by Grothendieck in SGS6, but nobody found, because we have no moving lemma basically. With rational coefficients, you can use K-theory, and then it's okay. But with integral. So I think this is the localization might be related with these problems. Okay, I think I've finished this series. Thanks.
So you said that S is regular but not necessarily over a field, and expect this to be some kind of Chow group. So which Chow group you are talking about?
Which one? Integrally you mean?
Yeah, so which Chow group?
Rationally, this is okay, right? Because you have here K0, and so this is just Chow group by using, cycles modulo rational equivalence. So rationally.
You're not talking about higher Chow group.
Now, one problem that you could ask is, do you have H2 and X S Z? I think you could build a map probably. This is an isomorphism. So if this was true, here you have a ring structure. So you will get a ring structure here.
Yeah, you are saying this is not known?
I don't know. This is true rationally, but not integrally. So the obstruction to the existence of a product here can be seen already here, can also be seen here.
Question in the same spirit. So we have the complex 0, 1.
Mm-hmm.
Yeah. So
block complex?
No. In this motives, do we have so Sim-Levelsky complex 0, 1.
Ah, C star of. I mean the singular. Yeah. Okay.
In any case,
By this delta star thing.
the
Yeah.
motive.
Yeah.
Yeah, we have the table motive.
Yeah.
So over every scheme, like even Dedekind as is Dedekind, is it known that it is the motive,
Yeah, this is really an interesting question. You can get something out of this for Z1 actually. So you can compute Hom groups in DM effective using this thing, and you can prove that in DM effective of say, actually you can prove that Z transfer S1 is isomorphic to GM minus 1, you might use S regular, or S a Dedekind ring. Okay, in the effective category. This is what, because you have Gersten conjecture for just GM. Okay. So you have a computation of effective motivic cohomology with twistor 1. You have the usual computation. Now, if you stabilize, you are lost because we don't know that cancellation hold. And actually, it should not be. It should not hold over a base which is of strict positive dimension. But nevertheless, just using that, you can, for example, prove that this cohomology is oriented, because then you'll have a map from the Picard group to the, here it's a stable category. So you have a map from the effective to the stable. So you have a map from Picard to the, and you have first rank classes, and then, yeah, so that's an important point actually. This cohomology is well behaved. For example, you have pullback and ring structure, but you have also push forward, I think, in for quasi-projective LCI maps, so with the correct behavior. But we cannot compute these groups. I mean, these groups here, we cannot give a presentation like that, or.
Yeah, just a question. The spectrum constructed by Spitzer is not known to be a real spectrum.
Which one?
The one which was constructed by Spitzer. It is not a real spectrum.
But there is an infinite structure or something like that?
I don't know.
No, I think so. I think he get a kind of highly structure on his ring spectrum, I think. But I would say that it's an infinite structure, but I'm not sure. Here, the good thing is that you really obtain a ring spectrum on the nose, as Topolog says. So that's also a good point. But yeah.
Are there any more questions? So let's thank Frédéric for his very inspirational lecture series.